just like a number can be a perfect square if it's the result of squaring an integer, a trinomial can be a perfect square if it's the result of squaring a binomial. Let's see what that looks like. And now I'm going to use just a generic binomial, capital A plus capital B or capital A minus capital B. But don't think of these as single variables, think of these as any expressions. So if I have capital A plus capital B squared, that's capital A plus capital B plus another A plus B. Right? Squaring something is just multiplying it by itself. Then first terms, I'll have an A squared. Outer terms, I'll have an AB. Inner terms, I'll have another AB. Last terms, I'll have a B squared. So if I take A plus B and square it, I end up with A squared plus AB plus AB is 2 times AB plus B squared. On the other hand, if I have an A minus B and square it, that's A minus B times another A minus B. First terms, I'll have A squared. Outer terms, that's A times negative B is negative AB. Inner terms, negative B times A is another negative AB. And then negative B times negative B is going to be positive B squared again. So I'll have A squared minus 2AB plus B squared. So I notice that my second squared term is always positive when I have one of these perfect squares. But then that middle term is positive when I started out with addition, and it's negative when I started out with subtraction. So I can recognize these perfect squares by looking for a couple of things. First, the first and last terms have to be the result of squaring something. So that means the coefficient is a perfect square number, and then we have an even power of the variable. Because when we square a monomial, we multiply all the powers of the variables by 2, so we'll end up with an even power of the variable. So we have two terms that are perfect squares, A squared and B squared. And then the middle term is the result of multiplying A times B, doubling it. It can be positive or negative. So let's take a look at some examples where we can identify perfect squares. And if we see perfect squares, we're going to use this, what's called a special form, to factor them quickly and easily. So here we have 4x to the fourth minus 12x squared plus 9. So first I'm going to say, do I have two perfect square terms? Well, 4 is a perfect square number. 12 is not. 9 is. Let's see if this first and last term are perfect squares. Right, 4x to the fourth. Well, 4 is 2 squared. X to the fourth is x squared squared. So this is a perfect square. And then 9 is 3 squared. Okay, two of my terms are perfect squares. Now, if this is a perfect square trinomial, my middle term, negative 12x squared, well, that's negative. It would have to be negative 2 times 2x squared. So this monomial times 3 this monomial. Well, let's see. Negative 2 times 3 is negative 12. And then I've got an x squared. Oh, that's what I hoped to see. Yes, that checks out. So as a perfect square, this is a minus b squared, where a is 2x squared and b is 3. My polynomial here is 2x squared minus 3 squared. And let's check that that actually worked, because I just directly wrote that down without going through my usual process for factoring a trinomial. So 2x squared minus 3 squared, that's 2x squared minus 3 times another copy of 2x squared minus 3. Multiply my first terms, that's 4x to the fourth. Outer, that'll be minus 6x squared. Inner, that's another minus 6x squared. And last, that's positive 9. Combining like terms, that's exactly what we hoped we would get. So that really checks out. 2x squared minus 3 really does factor 4x to the fourth minus 12x squared plus 9. Let's see another example. X squared might be a perfect square. Well, that's definitely just x squared. 16y squared? Well, 16 is 4 squared. Y squared is y squared. So this has the potential to be a perfect square with our a is x, our b is 4y, our middle term is positive 8xy. If this is a perfect square, that's going to have to be 2 times x times 4y. Well, 2 times 4 is 8, and then I've got an x times a y. Yeah, that checks out. This is a perfect square. We had addition in the middle term, so this is going to be of the form a plus b squared, where a is x, b is 4y. And so our claim is that x plus 4y all squared gives us our original polynomial, x squared plus 8xy plus 16y squared. And again, because we just wrote that down directly, we probably want to check. X plus 4y all squared, that's x plus 4y times another copy of x plus 4y. So x times x, that's x squared. X times 4y, that's 4xy. 4y times x, that's another 4xy. And then 4y times 4y, that's 16y squared. And so combining like terms, we'll have x squared plus 8xy plus 16y squared, which is exactly what we wanted to have. Now let's see a couple of examples where we don't have perfect squares. This one looks promising, right? My first term is a perfect square. X squared, that's just x squared. My last term is a perfect square. 4y squared, that's just 2y squared. But then my middle term, I have negative 5xy. If this is a perfect square, that ought to be negative 2 times x times 2y, which is negative 4xy. Those are not the same. So we can't continue to factor this as a difference of squares. This is not a perfect square. Now, that doesn't say that this is prime. We might be able to factor it some other way, but we can't factor it as a perfect square. This last example looks promising to begin with, right? X squared, that's just x squared. And we might think that we have a 9 here, but notice that we have a negative 9, right? Which is not the same as 3 squared or negative 3 squared. There's nothing that we can square as far as real numbers go and get negative 9. So the fact that both of our second and third terms are negative, we don't keep going. This is not a perfect square. So these last two examples looked promising. They looked like they might be perfect squares, but it turned out that they weren't.